Good morning, friends. I warmly welcome you in the series of Mechanics of Solids. We have started a series of a topic of shear stress distribution diagrams. In that series, we have derived an equation of shear stress distribution diagram. We have derived the particular equation and we have solved certain numericals. We have plotted the diagrams also depending upon the type of section. Today in this series we are going to solve some typical problems related to the shear stress distribution diagram. So now let us recall what we have studied up till now and what is the today's objective of the session. So now we learned in the previous session about the introduction to shear stress and the derivation of equation on shear stress. We solved certain numericals based on the fundamental equation. Objectives of this session: define the shear stress, draw the shear stress distribution diagram for typical sections. Now let us revise that we had studied up till right now in case of the chapter of shear stress. We have seen in the previous session about bending stress in beams. We have seen that a part of beam which is subjected to a constant bending moment and zero shear force, there will be only bending stress in the beam. The shear stress will be zero as shear force is zero, which is not possible in actual situation because the beam subjected to any kind of loading, it is subjected to the bending moment as well as the shear forces which is changes from section to section. This shear force leads to shear stresses. Hence this shear stresses will be acting across transverse sections of the beam. So these transverse shear stresses will produce the complementary horizontal shear stresses which will be acting on longitudinal layers of the beam, and intentions that we have to study this shear stresses and we have to study the variation of this shear stresses along the length of the beam, specifically along the transverse section. We have derived an equation for shear stress. Tau is equal to F A y bar by IB. F, that is the shear force acting at a particular section. A y bar, that is a whole, that is nothing but the moment of area of a particular area above a particular layer, and in which specifically A is the area above a layer, y bar is the distance of the CG of that area to the neutral axis, I, moment of inertia of the section, B, that is the base width available at that particular layer. Now we have studied the variation of the shear stress distribution along the rectangular section, circular section, I section, T section, triangular section, and today we are going some typical different section and try to see how the variation of shear stress is going to take care. Now start with the section. Beam having a square section with one diagonal as horizontal. Draw the shear stress distribution diagram for a beam of square section with one diagonal is horizontal. The beam is subjected to the shear force F at a section. So here a square section is there with we have. Along with that square section, it is to be placed diagonally, in which the one diagonal is horizontal. The section is subjected to the shear force F, and our intention is to plot the shear stress distribution diagram along that particular section. refer the particular figure. Here figure shows, clearly visualize, it is given a square section, but it is to be placed in such a way that the one diagonal is horizontal. Let the diagonal name is AC is horizontal and the length of that diagonal is small b. So it is very much clear that neutral axis of beam passes through this diagonal AC. So the neutral axis is passing through this diagonal AC. Now consider a level EF at a distance y from neutral axis. So please refer the figure. We are considering a one layer EF at distance y from the neutral axis or this AC diagonal. Why we have taken care of this layer? Because we know the fundamental equation, that is tau is equal to FA y bar by IB. Using these equations, our intention is to plot the shear stress distribution diagram along this section. Means what will be the value of shear stress at B, what will be the value of shear stress as layer EF, the value of shear stress at this section, at the section AC. So I want to find out the variation of the shear stress along the different sections. Hence let I have to take the one sample layer EF at distance y, and intention is to found out a generalized equation that what will be the variation at layer EF. Hence I am going to take a layer EF right now. So the area under consideration is of this triangular area, triangle BEF, because as such I am taking a layer EF. The formula tau is equal to FA y bar by IB. I have to take an area of triangle BEF, and y bar is the distance of the CG of this small triangle BEF to the neutral axis, that is the y bar. So now let us proceed further for the same. Now where AY bar is equal to moment of the shaded area about neutral axis, as we have visualized right now. It is nothing but the area of triangle BEF multiplied by the distance of CG of the triangle from the neutral axis. So let us refer the same thing on this tabletop, what this thing suggests us. So here the section which is given to us is like this. This is my neutral axis, as well as this is my one of the diagonal named called AC. Let us consider this layer EF. This distance is known to me, that is y. I have to take the area of this. So area is the area of triangle. This one, this is B, this is D. Now y bar is nothing but, let us, this is the CG, then this will be by y bar. Now area is the triangle. If this depth is known to us, let it is x, then area of triangle is equal to half into x into the width EF. This is the area, and y bar is nothing but the CG distance plus y, or we can say that available this height minus this distance, anyone we have to take care. So please visualize on this PPT. It is nothing but half into EF into x into the available total height, that is the half of the diagonal. The diagonal width is known to us, that is B. So half of that, that is the B by 2, minus the CG distance from the top of the extreme point B, that is the 2/3 of x. Now, we know that the ratio EF by CA, or that is AC, is equal to x by B by 2, and we can HU EF is equal to x by B by 2 into B is equal to 2x. So we are converting this EF, the value of EF, in terms of the value of x and B. So we have taken the similar triangle rule. Please visualize over here on this tabletop. This is known to us, that is B by 2. As per the similar triangle ratio, EF divide by CA, this width divide by this width, is equal to height x divide by B by 2. We know that this CA is B, and by simplifying this we can HU EF is equal to 2x. So we are converting the width of layer EF in terms of the height of the triangle. So we are putting the value EF as 2x. So AY bar is equal to half of 2x into x multiply by the same one, that is B by 2 minus 2/3 of x. Let us once again simplify in terms of the triangles. We got it x square bracket B by 2 minus 2/3 x. Now, I is the moment of inertia of the whole section about neutral axis. Now, we know that the given section is rectangular section. So, if you are referring over here on this tabletop, please tabletop, the given section is rectangular, but we are putting this rectangular section in such a way that the one of the diagonal is horizontal. So I will treat it as the two different triangles. This is one triangle, this is another triangle. We know that the moment of inertia of a whole triangle about its base is equal to 1 by 12 BH cube. B is the base, H is the height. This is the one triangle. So this is, if I will take the two triangle, so 2 into 1 by 12 BH cube is the moment of inertia for the whole section that we can got it right now. Now B is nothing but AC width, H is nothing but this width, that is nothing but B by 2. The same thing concept will be adopted over here. Please refer the PPT. 2, because we have taken two triangles, is equal to 1 by 12 BH cube, that is twice into B by 2 cube by 12. It is not a square, it is cube over here. So we can got, by simplifying this, B raised to 4 by 48. B is nothing but the actual width at the level EF is equal to twice x. So now substituting this value over here right now in this equation, because B is not over here B. In the original equation, tau is equal to, please come on this tabletop because it is very important to understood over here. Tau is equal to FA y bar by IB. This B is nothing but the width available at layer EF, and that is nothing but 2x. So if you are referring over here in this figure, this is nothing but 2x, and this is the value of B we have to put over here. In this case, this is B is the width of layer. So by putting that value on this PPT, 2x over here, and simplify, that is f into AY bar, that is x square bracket B by 2 minus 2/3 x divided by B raised to 448 into 2x. By putting all this value, and we'll just simplify this one, we can got an equation tau is equal to 4f by b raised to 4x x bracket 3b minus 4x. It's equation number 1. This equation gives the variation of shear stress at the layer EF located at distance x from the top extreme fiber. Now at the top x is equal to 0. So now when x is equal to 0, this 4f by b raised to 4 into 0, the answers come 0. So we got the tau is equal to 0. So at the top extreme fiber, if we please refer over here on this tabletop, at this location, at this section and at this section, the value of tau is 0. It is the meaning of the statement as x is equal to 0, the value of variation of shear stress at B and at D is equal to 0. Now, at the neutral axis, x is equal to B by 2. So now we have to put the value x is equal to b by 2 in our simple equation of tau is equal to 4f divided by b raised to 4 into x bracket 3b minus 4x. We have to put the value x is equal to b by 2. Our intention is to find out what will be the value of shear stress at the neutral axis. So x is equal to b by 2. By putting this over here, that is 4f divided by b raised to 4 into b by 2 bracket 3b minus 4 into b by 2, we got 2f divided by b square. This is a term which correlate in terms of the shear force acting at that particular section and the width of the diagonal AC. Now, this is the value of shear stress variation at neutral axis. Right now we do not know what is the location of the maximum shear stress, because in case of the rectangular section we know that the maximum shear stress which has been taken care at the neutral axis, but that doesn't mean that we are changing or we are